quantum computing and simulations of trapped ions.
Yeah.
Close enough. Thank you. Okay, so I'm happy to be here, and sorry I missed most of the rest of the day, but I guess this is the last talk of the day, and we'll conclude with a hardware talk. This being the building of quantum information processors using atoms, individual atoms, and these are charged atoms, trapped ions. And there's a picture of sort of the best of everything in terms of the number of ions that we are currently manipulating, about 50 or so in a linear ion trap. I'm not going to talk too much about that. I'll return later to the most advanced chip traps that we're using. This one's built by Sandia. And interestingly, this is the only quantum computing hardware that uses conventional silicon fabrication. This is a conventional silicon fabricated set of electrodes. It's plated with gold, but there are no individual impurities. It's room temperature system, so there's nothing really exotic here. Of course, we afforded that because the quantum system is not in the silicon. It's not solid state, and this is why why the qubits are so good. They're atoms. They're atomic clock qubits. And so I'll talk about this as we go through. So this is a you should always be careful picking claiming that you know what the winning hardwares are. This is from an article in Science, a review article a few years ago, plotting several of the leading candidates to build quantum computers. And I would say these top two, superconducting circuits and trapped ions, are really, there's a big gulf between these two and the rest of them. And it's because these systems are now called systems. They're being built into systems. They're no longer physics experiments. I think that's really important in this field, that we have systems that can be used by a third party, somebody that doesn't know or care what the qubits are made of, but like any computer can use it in an abstract way. And indeed, we're seeing these things being built up, and there's big investments in both these technologies. So it's no surprise that those two are sort of leading candidates now. To back that up, this is a plot of the error per 2-qubit gate over time. And we can see in these two technologies, things are getting really good, really fast. And the two things I want to mention here is that the state of the art is around 3 nines in these technologies. We think we know how to go further. But you should also sort of dispense with this plot right away, because all of these data points involve exactly 2 qubits and no more. And so that means there are lots of other errors that will pop in when you want to scale the system. When you want to build a system, this plot's sort of irrelevant. Okay. And maybe we've heard a similar similar version of this in the superconducting technology from John's talk. Okay, so trapped atomic ion qubits, as I mentioned, the beauty of atomic qubits is that they're standards. Actually, literally, they're frequency standards. They're atomic clocks, so they're identical. They're more identical than you can make anything identical. That's why we use them to define the second. So the qubits are done. They will never be improved. They're way better than we need to be. We can make qubits identical to a part 10 to the 15 if we really need to. Fortunately, we don't need to. So that's not the issue. The issue, of course, is that while the atoms are perfect qubits, it's the control system around them that is where all the challenges are in this type of a qubit. And in that sense, it's sort of complementary to many solid-state platforms, where the controllers, again, can really leverage the VLSI and solid-state fabrication over the last several decades. And their materials will improve, but always will be limited by the fact that each qubit is a man-made qubit, and there are inhomogeneities and so forth. That's not the problem here. So with trapped atomic ions and atomic qubits in general, we can read them out. I'm not going to go into too many details here. Maybe you heard a little bit about this before. We can read them out using laser fluorescence. Depending on the qubit state, the atom fluoresces or it doesn't. And you can get a near perfect measurement per qubit in a single shot. And by near perfect, I mean the record is like 4 or 5 nines of fidelity. And if you only have 100 qubits, you don't even need that. So again, there are lots of things when you build the system. You shouldn't go too far in any one dimension. You don't need 6 nines of anything yet unless you have 1 million qubits. I mentioned we can do high fidelity entangling gates. I'll talk a little more about that. The coherence times are incredibly long. They've been measured to be at least 10 minutes. It's probably longer than that. And the system itself, indeed, the bad news is we have lasers all over the place, and the systems are held in a vacuum. These atoms are suspended above this chip in a vacuum chamber because you can't have air colliding with the system. So that's a little exotic, a little difficult to think about building a future computer with lasers and vacuum systems. But that's the price you pay for having pristine qubits. But we can do lots of things with a room temperature apparatus, which is another bonus. OK, so I'm going to talk about a couple of different topics here, and they're quite related. And the first one will be, how do we make gates between these ions, these lasers that I mentioned? How are they used to wire together these atomic qubits? And the story is actually, it's a very, a lot of it's classical physics. We're applying forces to these atoms using lasers, very much like optical tweezers push around dielectric bodies, cells, or whatever. In this case, I totally skipped over ion trapping technology. Here we have a linear chain of about 20 ions or so. They're separated by several microns. That separation is a balance between the Coulomb repulsion and the external confinement. And in this case, it's obvious that one of the three axes of confinement is very weak compared to the other two. And that's why they line themselves along a linear chain like this. So we're going to store qubits inside the atoms, actually in hyperfine states. I didn't talk about that. These are effective spin states within the atoms. But they're going to couple. There's no wires, obviously, between the atoms, but we can couple them through their collective motion, mediated by the Coulomb interaction. So the idea is if we want to entangle any pair of these ions in the chain, we can send a laser beam, specially tuned and focused, to individually address those target qubits that you want to entangle. And importantly, these laser beams will apply a force that depends on the qubit state. We call it a state-dependent or spin-dependent force. So if the atom is in the state 1, it moves up, and if it's in the state 0, it moves down. And of course, if you have a superposition of 0 and 1, then you're splitting the atom in two places. You're making a little interferometer that way. And the whole point here is that the Coulomb interaction is nonlinear, and that is, if you look at the four possibilities of these two states, of these two qubits, if you're in 1, 1, or 0, 0, their Coulomb interaction is exactly the same as it was. But if they're in opposite states, then the atoms are a little further apart, and there's a tiny defect in the Coulomb energy. It gives rise to a dipolar 1 over r cubed force. This is in one regime. By the way, you're going to ask, what happens to all the other ions? Isn't it like pendulums connected by springs? If you wiggle one pendulum, they all feel it, and that's true. This math works in the limit where the entangling gate is really fast. It's so fast that we push the atom and then we return it in a time faster than any of the motional frequencies. And in that case, it is the price you pay. It's good because it's fast, but the price you pay is then you have a range problem. The gate only, you can only entangle over certain distances. And if you look at the four possibilities of those states, again, the two states with mixed states of qubits suffer a phase shift, the same phase shift, and that's why it's nonlinear. And when that phase shift is set to pi over 2, it's equivalent to a controlled NOT gate. In a different basis, it's fully entangling. Okay? And in fact, this actually is the physics, the basic physics of what goes on. Except that we don't do it this way. We don't do it in the fast way. We actually do excite all the motion. And that's a little bit of a pain in the butt, but it's a classical pain in the butt. Because we have to take care of all those modes of motion, and we shape our laser pulses in a very non-trivial way. We pre-calculate laser pulses using the classical physics of this Coulomb interaction to decide how to make sure that all those modes return to where they started, and there's no entanglement left in those modes. Because we only want entanglement on the spins. Okay, the other one thing I put under the rug is that we actually do this in a different basis, the X basis, not the Z basis, like this Z gate here. So our native, the best gates in trapped ions are called Mollmer-Sorensen gates, or I call them Ising gates. This is the evolution operator. It's just an XX interaction. And by setting the time of those laser pulses, you can realize this gate, it's fairly slow compared to solid-state systems. It's from 10 kilohertz to a megahertz, these gate speeds. And the fidelities are depending on the system. If you have only 2, you should be expected to do better than 3 nines, of course. Okay. So this is sort of a variation of the physics first studied by Ignacio Serac and Peter Zoller a long time ago in 1995. And the Mollmer-Sorensen improvement of that basic idea is what everybody uses today. So I want to talk about a very simple experiment that we've started a few years ago to try to scale this up, again, dealing with all these modes of motion. And in doing so in this experiment, this is a schematic of the experiment, the laser beams that drive that force are actually they have to be counter-propagating. But one of them is focused down to hit the ions, the other one's uniform. And the brains of the operation is really this multi-channel optical switch. It allows us to control the amplitude, frequency, and phase of any number of beams. In fact, this has 32 channels. Another example of leveraging the silicon fab industry, this is made to etch higher levels of CMOS, actually, to have lots of beams, 32 beams. And a company, Harris Corporation, makes this, and they make it for us now. Instead of cutting CMOS wires, we're focusing on individual atoms. And so with 5 qubits, we can put all 5 beams on, we can put individual beams on, or we can put all the 10 possible pairs to do all the 10 possible 2-qubit gates. And unlike the 1 over R cubed example I showed before, here this is fully connected. In fact, the best gate, highest gate fidelity, the fastest one is the one between 1 and 5 that were furthest apart. And this has to do with a normal mode that has the end ones moving a lot more than the others. Again, it's a small system, so you should always think about how this will scale, and I'll comment on that as we go. What we were a little bit surprised at in this experiment, maybe we shouldn't have been, is that it allowed us an opportunity for once in atomic physics to enjoy the full stack of this tiny quantum computer. I've been operating my whole life pretty much way down here, playing around with the atom, laser interactions, and turning screws to make vacuum pumps work, and so forth, and lasers, and lasers. I mentioned at a higher level, we need to shape these laser pulses classically, and so there's some classical overhead. It's linear with the number of qubits, so it's not so bad. The prefactor is like 8, though, so 8n. Well, when n is 5, it's not so bad, but it's not so bad, so we think we can scale well beyond 5 here. But then we go up one notch, and we have these XX gates and rotation gates, but the textbooks have controlled NOT gates and Hadamard, so we need to compile. If there's an algorithm at the very top, some textbook algorithm, it's usually in the textbook gate language, and we have to do this compilation step to interpolate. And so when we get things set up in the morning, we can actually run from the very top for many hours, which is really cool. We're sort of abstracting away the device, and that's again, it shouldn't have been a surprise, I guess, but the performance of this was such that we could do some pretty fun things. And so one example, again, they're textbook gates, small algorithms with just a few qubits that we can sort of test the system on. And these Oracle type algorithms are actually nice benchmarks for small systems. They give you a yes or no answer. It doesn't mean that you can understand all the errors that were in there. But when you're testing small systems, algorithms like this, even though the Bernstein-Vazirani algorithm is full of Clifford gates only, you could argue about the depth of entanglement and all that. But in any case, there is entanglement in the algorithm for all these oracles, and it's a good way to benchmark the system. So Bernstein-Vazirani, to refresh your memory, is a n-to-1 bit function where we don't know some bit string that is hardwired in the system. It's the oracle. It includes a C. And the question is, what is that n-bit string C? And classically, we of course have to evaluate every bit of C using separate experiments. So there are n evaluations, but quantum mechanically we do it just once. You all know this, I'm sure, by having superposition. So this is a circuit diagram for a 4-qubit Bernstein-Vazirani algorithm. The 5th qubit, like many algorithms, it's an ancilla qubit. And you can see the structure is very symmetrical here. And the oracle basically puts a C0 gate wherever the C bit is high. So this is an example for the 1111 oracle. Of course, there are 16 possible oracles. And then at the end of the day, when we measure these the first 4 qubits, C comes right out, just in that structure there. And so in our 5-qubit system at Maryland, we built 16 circuits here with each of the 16 oracles, and we made a simple measurement of the output state, single shot, with the single shot efficiency is at about 99.2% per qubit. So you can see the errors are not 0. In the end, the probability of success was in the 90% range, 80 to 90% range. Not unreasonable, because these gates, the C0 gates, have 6 rotations in 1 Ising gate, and we have the Hadamard gates have 3 rotation gates. So there's a lot of gates here, actually. And the way errors accumulate, it's not unreasonable to expect that. So we wanted, of course, this to be a 1 along the diagonal. Okay, so the reason I'm putting this up is that we got a call from our friend Martin Rottler at Microsoft, who was playing around with the IBM Quantum Experience. You know, they have abstracted away their hardware, and you can get this on the cloud. And they ran this algorithm. This is Jerry Chow and Jay Gambetta, who engineered the system behind them. And they ran the same algorithm on the IBM system and got similar results. You know, their gates are not as good as the ion gates, but decent enough to see the clear correlation between input and output state. The real key difference in these two systems is the connectivity of the qubits. And with only 5 qubits, you could argue connectivity doesn't matter because the system's tiny. But this is a unit cell of a square lattice, of course. And their connectivity is pretty weak here. And there's an architectural and a computer science issue here. How do you assign qubits to such a graph? Here, it doesn't matter. We can do any gate. Here, it's obvious that the 5th qubit should be the middle because it's the one that needs the connections to all the others. So it's another example of theorists at the very top doing algorithms and compilers. They need to know the hardware. They need to know aspects of the hardware. Maybe some of these gates have errors, and you want to not use those. Some of these connections could have errors. You don't want to use them so much. So one other example of an algorithm, this is another Oracle algorithm called the hidden shift. And this is where Martin Rottler really had troubles. I think he had something to do with the original version of hidden shift. Here, you're given 2 functions, and they're the same functions. It's just that the inputs are offset by some unknown string, s. This time, you need exponentially many. You have to evaluate about half of all the inputs to triangulate and figure out what that shift was. Quantum mechanically, once again, just once. In a single shot, you can get that. And this is an example. It's a 5-qubit circuit, and these are it's a 4-qubit hidden shift algorithm. There is a 5th qubit I didn't draw here. But this is a certain function. It's called a bent function. Almost doesn't matter what the function is. But the shift, once again, is encoded in this oracle in a certain way. It's maybe not so obvious. This is for the shift 1010. And you can see, in general, this algorithm requires more connectivity. And this is the result in the 2 systems. Again, just 5 qubits. Once again, this is actually a deeper circuit quite a bit in our system, so the errors are a little more, 80% or so. And the IBM system, it really, really took a nosedive. And of course, the reason is because it's not well connected. So the lesson there is connectivity really matters. Now, you could also argue that this is probably the worst example of the IBM system, because when they build their square lattice, it's going to be more powerful, and that's certainly true. But just the point here is an architectural point. Connectivity really matters. And we don't have a cloud, but we have, again, grad students and postdocs that go down in the lab in the morning, they tune the system up, and then in the afternoon, it's kind of fun. They can run from a laptop or from their PC controller for many hours in the afternoon. So this system could be on the cloud, not yet. And we've had fun running lots of other, mostly Oracle types of algorithms. And again, they're all trivial because we're talking about just a few qubits. And the gate depths here, this simulation of a few-site Fermi-Hubbard model actually took the most gates we've done so far. But I want to comment briefly on one involving 7 qubits. We're moving to 9 as well in this system. And in the 7-qubit system, this is a physics result, not so relevant to quantum computing maybe, or maybe not. If you want to make a quantum computer in a black hole, you might want to know about scrambling. Quantum scrambling, as you might know or have heard, scrambling is a subtle concept that's more than just entanglement, but it involves information that totally diffuses in the entire Hilbert space. And it's thought to occur in black holes. If you want to model a black hole as a unitary process, we think of black holes as being the fastest possible scramblers, information everywhere. It's sort of like decoherence, except it's a closed system. So it's not really decoherence. But the structure of entanglement in a scrambling unitary is incredibly dense, very deep. And there's lots of work on this, connecting it to the black hole information paradox. Patrick Hayden, John Preskill, and Lenny Susskind and collaborators as well. So there are some approaches to measure scrambling by measuring so-called out-of-time order correlators. If you take a quantum system, you evolve it forward and backward in time and make correlation measurements, you can say something about how this system scrambles. And in fact, if your correlators decay, then that's an indication of scrambling. Anytime a signal decays, and you're trying to show some physics, you have to be careful because there's lots of reasons signals decay. And so the difference in this experiment is that it's a positive test for quantum scrambling. It involves a circuit. It's a very simple circuit, 7 qubits here. And we have our unitaries. There are only 3 qubit unitaries, so these are pretty small black holes. But we need to implement the unitary and its inverse, which is if it's a circuit, it's not hard to do that. And the idea here, and this is pointed out by my collaborator Norm Yao here in the audience from Berkeley, and Ben Yoshida from Perimeter, that if U scrambles, then you can make a circuit that will give rise to conditional teleportation of an unknown state. So the idea is you prepare an unknown state here, all the others are initialized to 0, and if and only if this unitary scrambles, based on a measurement of any of these bell pairs, or you can hardwire it with a Grover circuit. We've done both of those. In any case, based on some conditions on these qubits, that unknown state gets teleported here. And the fidelity of the teleportation tells you whether it's scrambled or not. And the good news is if there's decoherence or other things going on that's bad, or even if U and U dagger aren't exactly the inverses of each other, then that will only cause the measurements to have a lower yield. It won't affect the fidelity of teleportation. So in that sense, we've separated the scrambling aspect of our signal from the dirty stuff. And by the way, you can't read this, maybe I did that on purpose, but the unitary we use is a very general one. It's sort of a permutation unitary, a fractional permutation unitary. And we have rotations in here. And what's cool about this unitary is that it has a parameter theta. And when theta is 0, there is no scrambling. You don't expect it. When theta is pi over 2, it should be maximally scrambling. And when we measure the teleportation fidelity, again, if you're less than a half, then there is no the fidelity. I mean, fidelity of a half is like having 0 teleportation, because you can classically move information with a fidelity of a half on average. And we can see as we increase theta, indeed the teleportation fidelity goes up. And it doesn't go up to 100% because this is a pretty deep circuit, as always. Errors are adding up. Just an example of what you can do with lots of qubits. And of course, when we get 64 and 128 qubits, we're going to continue along this path of looking at scrambling in much more complicated systems. And so this is some data and background there is in this recent paper. OK, so now I'm going to, I guess, simulators was in my title officially. So fortunately, the physics of how we make a simulator versus making a gate-based trapped ion system is almost identical. Here, we're simply going to apply, instead of focusing laser beams, we're going to hit them all with a big fat beam. And then we have an all-on-all icing interaction. And instead of having individual beams hit them, we have 2 fat beams, which, by the way, is a lot easier in the lab. And we end up having a full all-on-all icing coupling here. And we can apply a transverse field in any direction. That's easy to do just by putting multiple tones on these laser beams to flip the spin simultaneously along any axis. Now, importantly, this J matrix, the icing matrix, it's long range, and it falls off with a very good approximation according to a power law in distance. And we can vary that power law in practice between about 0.5 and 1.5. In theory, we should be able to go from all to all to 1 over r cubed dipolar. The sweet spot's between 0.5 and 1.5, but it's pretty long range. And the technique that we use here that we don't use in gates is that the motional modes are only virtually excited, where this force is way off resonance. So you can adiabatically eliminate the phonons. And that means that the speed of this operation is a lot slower than the gates. So instead of 10 to 100 kilohertz, it's more like 1 kilohertz. So it's slowing down the whole system. But it's fully connected as well, and we can go out in long times. If you want to calculate gate depths, it's large, even though these aren't gates. So as a very simple example, again, this is not exactly an icing model. It's a so-called XY model or a flip-flop model. We can add multiple tones to get that as well. And what's neat about this Hamiltonian is that the excitation number is conserved. If you flip one spin, and if 2 spins flip, then the number of spin-up atoms in the chain is the same. And so in this experiment, this is a dynamics experiment, and it sort of has generated lots of other types of experiments like this, studying the dynamics of these long-range interacting systems. Lots of entanglement, of course. Here we started with 1 atom in the spin-up state, or 1 state, all the others in 0. Now when we quench to this Hamiltonian, we're going to always have only 1 bright atom, 1 spin-up atom in the chain. And when we let the system evolve for what we would say is a decent gate depth, if you want, this excitation is hardly moved. This is an average, of course, of a few thousand runs. And in every single shot, the excitation appears in some place, but it's mostly here. And you can see that it sampled the entire, even the last one here, it sampled the entire chain. Very complicated dynamics here. And if you look more carefully at something, and we'll call this order parameter the position of the excitation. So in the middle would be 0. That would be -1 where we started, and this is +1. You can see over time, ignore the brown. That's just an averaged version of the data. The raw data, the blue here, we see that the position stays to the left, and it seems to stop evolving. Now, under the influence of this long-range interaction, there's something expected called pre-thermalization. So the system's closed. How does it thermalize? Well, when you trace over subsets, you can think about an individual spin thermalizing to the rest of the bath. But if you look at the energy spectrum of this long-range interacting system, especially for small alpha, where the range of the interaction is even longer, there's always one state that has a tiny energy gap. And the point here is that gap is getting really small, and it takes forever for true thermalization. If we could observe out to 3600, we expect that blue line to go to 0. But it does plateau, and that's, for lack of a better term, been called pre-thermalization. And so using this technique, our group and other groups have done lots of experiments with between 5 and 200 trapped ion spins in different systems, all in the guise of quantum simulation with this great control. It's not a quantum computer, but by some arguments, we're doing things in some cases that are very difficult or even impossible to calculate otherwise. Let me give you an example of that. The last one here is a quench experiment, and it's something we call a dynamical phase transition. I still don't know exactly what that means, but it's not an equilibrium state. So when you talk about phases, we're not talking about equilibrium phases. Here we prepare all the spins along the x-axis. This is a block sphere of any one of the spins. But we quench it to this transverse icing model, all-on-all icing model. And then we simply measure along x. It's one of the simplest experiments we can do. And depending on the value of b over j, we get interesting dynamics. When b is really small, the atoms are along x. They're already in an eigenstate of this Hamiltonian if b is really small. And so nothing really exciting happens. They stay ordered. And they don't evolve so much. This is the measurement of the average magnetization over all the chain. I think this is, I don't know how many spins this is. I think this is maybe 20 or 25 spins. At high values of b, when b dominates, then these spins precess around the z-axis. And you can say that this is not exactly thermalization because the rotation frequencies are all different a little bit on the spins.
What alpha?
Pardon me?
What alpha?
0.6. Yeah, it's pretty long range. Pretty sure of that. I'll have to look that up. But when we add lots more spins, it turns out this phase transition, by measuring the mean magnetization, is it's smooth, not as sharp as we'd like. And in fact, in theory, Alexei Gorshkov, our collaborator, has helped us understand in theory, yeah, it's going to evolve very slowly. So we looked at a different order parameter. We looked at a full n-body correlator here. And this is data with 53 qubits. And we see that as we increase b over j, we see a minimum in the maximum domain size if we average over many, many runs. And I won't get into too many details here, but this is just data here. The line here is just a fit. We don't understand why it should be that way, and we certainly can't calculate where this phase transition occurs. It's sort of an infinite temperature phase transition. It's very strange. So that's why it's called a dynamical phase transition. And you can argue that we can't calculate this. We can't prove that we can't calculate this, but we can't calculate it. OK, so why 50? Well, it turns out that the vacuum, I mentioned we have to pump the air out. Turns out that at room temperature, the vacuum is not perfect. It's never perfect. But at room temperature, there's stuff in the background. And a number easy to remember, and it's a beautiful atomic physics collisional calculation. Each atomic ion suffers a collision every hour at room temperature, given this typical background pressure. So we can just kind of brute force turn the pressure down by going cold. So this is an apparatus that's at 4 Kelvin. And 4 Kelvin these days is a lot easier than it used to be, but still we need optical access, so we don't exactly want to do this. So we're kind of kicking and screaming here. But we don't care about the cold temperature so much. That does help on background, but mainly it lowers the pressure because everything sticks to the surface. And at 4 Kelvin, this 1 hour number becomes weeks or something per atom. So this is an image of, you'll see a little kink in the middle of the image. because I think the chain was so big that they had to move the imager over to capture both halves of it and stitch it together. There's 121 ions, and they stay there all day as long as we're in the lab. Importantly, there's a gap over here on the right. We don't know for sure, but this is either a doubly ionized ytterbium or it's a different isotope of ytterbium. That's our, I don't think I mentioned ytterbium, that's our ion. There's a different isotope that's not fluorescing at the right frequency. And what's neat about this, what we like about this gap here is that gap stayed in the same position all day, as long as we had these ions in the trap. That means they never reordered, and that's important. So when we want to scale beyond 50 or so, my guess is that we're going to need to go to 4 Kelvin. Okay. Now, you might ask, well, there's 120 modes of motion you have to control. Yeah, that's going to be an issue. If we wanted to build our 5-qubit system up to 121, there's some issues there, and we have yet to work them out. But we believe that we're not going to have a fully connected system over this chain, but it will be connected plus or minus 10 or 20 ions is my guess. So, you had a question?
I was curious what your method is for, I guess, modeling the modes that you get. I mean, presumably it's something that's feasible at 5 qubits, but then if you're trying to scale to 121, I was just curious what that is.
Oh, yeah, I gloss over so many things. So these atoms in a trap, you can think of them as a molecule. They're a bunch of atoms bound, right? Of course, they're bound because we push them together. And so you can do Raman spectroscopy on the vibrational modes. They're normal modes. They're harmonic oscillators. They're laser cooled to the ground state, so they're very clean. And we can just simply measure the sidebands, the response of these chains to forces. And we take a Raman spectrum. With 121, there's a forest of modes. We've taken data with up to about 40 spins, and just we can identify every mode. And you might ask, do they drift and so forth? That's a good question, and these are things that we have to work on as we scale the system up. Yeah. Yeah.
Are you able to do multiple 2-qubit gates at the same time then for those very long chains?
We have, again, we've just started. We only have one working system, and it's unfortunately it's tiny chains. We only have so many laser beams. We've done parallel gates on multiple pairs at the same time. And again, it's a classical math problem. It gets a little more, there are more constraints, so it's a little harder to do classically. But again, with 5 or 7, I don't want to speculate on where that's going to end. My prediction is that even with 121 ions, we're not going to have to, the laser pulses are not going to add in complexity. And the price you pay is that they're also going to be somewhat local. So you're not going to be able to do a gate between this one and that one, but you can do between this one and maybe that one. There's going to be some distance over which things work well. And again, this is yet to be mapped out. But I wanted to, as I conclude, I wanted to spend a few moments talking about how we scale beyond this, because I really don't imagine having more than several hundred ions in one chain. In fact, 50 or 100 I think might be sufficient. So the idea, of course, is to make a modular, scalable system where we have a bunch of collections of small chains, small being somewhere between 5 and 100 or something, would be my guess. Now, I would argue that anything complex, if you want to grow it, is going to have to be modular. And we see this, of course, in classical computing, multi-core processors. You don't make a bigger chip, you make more chips and connect them together. And the point here is you're limiting connectivity, but you're still growing the system. And that's what we can think about exploring, and certainly in the trapped ion system. Now, my colleague Dave Wineland many years ago thought immediately that we're going to need to make very complicated ion traps where we can shuttle ions around in space. And here, the modularity is very clear. You could have a bunch of registers where you do computations, and then you physically pick atoms and move them around. Now, all of the simple experiments have been done with shuttling atoms and maintaining entanglement and so forth. The hard part, of course, is to make the electrode structure, and it's not going to be a typical university-type experiment. It's going to be one of these chip traps I showed before. And my prediction is this will allow us to scale from 50 in a module to maybe a few thousands on a single chip. Again, we don't have that chip yet, and it'll almost certainly have to be at 4 Kelvin. There are loading issues and so forth. A lot of engineering issues that we're going to come up against. In the long run, and this isn't quite ready for prime time, we also can take advantage of the optical activity of these qubits. We use that for readout and, of course, making the gates. But we can map the quantum information itself onto single photons, either their polarization or their color or their time delay. Many protocols for that. And you could imagine having a bunch of registers of individual sets of whatever, 5 to 100 or even 1,000 ion traps that you've shuttled within one. And then you can map them onto others by mapping a given subset of these ions onto single photons. And the photons Here we have a non-blocking cross-connect switch, fiber beam splitters, and a CCD array. All this is classical. It exists. The question of integrating all this on the ion traps, the hardest part is right here, just that interface. Because we have an isolated quantum system, and now we want to collect photons from it. That means we need to get optics very close to these atoms, and that's why when we started these experiments with only two separate modules about a meter apart, we were connecting them at a ridiculously slow rate of about 0.001 hertz. Every 10 minutes we would get an entanglement event. Now things are a lot better. We got 4 orders of magnitude simply by improving the optics, and because there are 2 photons, any little improvement we get to square it. So we're at about 10 per second now. We think we know how to push another few orders of magnitude. And when we do that, I put this up here, when we do this, it becomes comparable to the speed of the gates inside the module. And that gives you lots of opportunities for maybe making it more optically intensive. So we need to get there to show that. But as it gets better and better, it will impact the high-level architecture of local versus remote entanglement. The big problem, and I know you're thinking this if you've seen an AMO lab, the big problem in all these experiments is that they look like this, which is a nightmare. And I'm an AMO physicist. In my community, people are usually proud of experiments like this. Like, look what I can do. I can put lots of cables together. I think it's ridiculous. It's embarrassing, and it's pretty much there's no progress in a lab like that. So fortunately, over the last few years, we've been afforded the opportunity to do a system top-down version of this, and without much exaggeration at all. Everything you see here, except the grad students, can be compressed down to about a meter cubed. If you know what you want to build, you don't need XYZ knobs on every optic. So this is a very tightly integrated system. It's funded through IARPA, and it involved, I mentioned Harris on the modulators, also Coherent makes our laser, Cold Quantum makes vacuum chambers, AOSense makes the CW lasers that we tune for detection and so forth. And this system is still underway, but we have 32 beams. We don't worry about the ions. We can probably trap 50 to 100 ions in this trap made by Sandia, but it's more the control from the outside, the laser beams, that are the tricky thing. Oh, by the way, a lot of this table here, probably about half of this table, has been compressed to a single drawer made by AOSense. Again, if you know what you want to build, it's very easy to build it small. And by the way, when things get small, they also perform better. And if this looks like something that is stretching what we can do at a university, it is. And in fact, we can't hope to kind of maintain this pace at the university. So there is a startup company that's using this this hardware as the ground floor of what they want to do. So IonQ is just off University of Maryland's campus. We have about 30 people now, and only a third of these people are quantum people. Most of them are FPGA engineers, RF, microwave engineers, some silicon fab people, a little bit of that. We fortunately we don't do our own fab. And of course, software, API folks that will put a system like this on the cloud. That's our goal at IonQ. And this is actually a picture from one of the IonQ labs. Again, this can all be condensed if we need to, but we don't need to. We're not going to deliver this. But there's the meter cubed version inside the guts over at IonQ. So I'm pretty bullish that we can certainly push to 32 at room temperature. I have no doubt about that. Going to several hundred by shuttling through more complex traps. All the fundamentals are there, and I think you're not going to build 3200 unless you build 32 first, and maybe stamp those out and think about these modular approaches I talked about before. So my last slide, I like to quote my colleague Bill Phillips. In fact, I noticed this in one of Scott's. This must be your version of the quantum computer, but Bill is fond of saying that.
It is what they look like.
Literally, yes, that's right. It's a really big atom there. So Bill is fond of saying that a quantum computer, this is no news to the folks in this room, but a quantum computer is more different than a classical computer than that classical computer is to the abacus. And what he means here is theoretically, these are both Turing machines, and they follow the laws of classical physics, even though they don't look alike, and you would never factor a big number using an abacus, a really big number. But on the hardware side, there's no reason to expect that a quantum computer will look anything like a classical computer. It's so different. It's not just a more powerful classical computer. It's so different that we need to look at radical types of hardware because it's very exotic to have such isolation of any quantum system. So I hope as time goes on that other qubits come to light in different forms, and we're able to engineer them. So with that, this is a recent picture of the group. And I will acknowledge a couple of key collaborators, Jung-Sang Kim at Duke, who's an engineer. He's been working on ion traps for over 10 years, really from the systems level. And also my colleague Norbert Linke, who's now a faculty member at the University of Maryland. Thanks for your attention. John?
Have you done things like random benchmarking on your 5-qubit device for single and 2-qubit gates to get the rough performance there?
Yeah, we have, on single qubit gates, yeah, there's a pretty well-established method for that. And that actually, Jung-Sang Kim has done more than we have on that. And I don't know what the number is. I think it's 5 nines or something ridiculous. For single qubits. For 2-qubit gates, we're starting to do, working with the group at Sandia, this gate set tomography. And I have to say, it doesn't seem to be a complete.
Why can't you just do a randomized benchmarking like we've done for superconducting qubits if you have if you can run a general purpose algorithm?
You'll laugh at me for my answer, but in that 5-qubit experiment, our AWG only has a depth of like 100 gates. It's stupid. So with our upcoming system, we'll have much more to go. So not a very satisfying answer. But.
Can you say something about the errors and resetting of qubits, et cetera?
Yeah, I skipped so many things. The errors in our system are completely dominated by induced errors from our lasers. The lasers either move around in space or their power changes in time. And you can't always predict that. And so that ends up being an effective noise on the gates. It's not decoherence really, but you can think of it as decoherence if you want. It's a classical noise source on the qubits. The readout, okay, there are many ways to answer this. The readout I mentioned is very clean, but the one thing I swept under the rug is that we so far, in everything I've shown, the readout is global. We read out all the qubits at once. Your question seems to be leading toward error correction, where you might read out a fraction of them, and based on that, do some kind of correction operation. We don't do that yet. With the 32 system, we're going to be able to do that by shuttling ions around, and we're going to have multiple species of ions in there where we can read out one species qubit without touching the other. So I'm not sure I've exactly answered your question, but readout errors in general are not what we worry about. Initialization is even better than readout. It's called optical pumping, and it's very hard to measure when you're better than 6 nines of accuracy in your initial state. We're always limited by the readout inaccuracy, which is more like 3 nines or 4 nines. I don't know if that helps.
To zero?
Yeah, that's optical pumping. That's super clean when you do them all at once. If you want to reset just one, it's a little tricky. Yeah.
So that was my question, is about so resetting an individual qubit, or you're trying to do some algorithms, so you need to get in solos, or you need to measure those. Is the limitation basically the lasers that you have to focus down and not affect the other qubit? I mean, what are the?
Yeah, it's crosstalk. Now, measuring is harder than readout, even though measuring is harder than resetting, I meant to say. Resetting, you don't need to get the information, and it only takes about 10 photons to get a very high probability of resetting. Measurement, you need to scatter maybe 1,000 photons. And if you're focusing on just one qubit, some of that light can spill out and hit the others. So resetting, I don't worry about so much, which is good. If you want to do error correction, actually you only need to reset as long as you have gates. It has an overhead of gates. But you're both thinking about error correction, I guess, right? My feeling about error correction, and this will sound naive maybe, is that it won't play a role anytime soon in anything we do. That's probably for the whole field. Yeah, Patrick.
This playing with this exponent alpha that describes the decay of the interactions is like a little like going from one-dimensional to infinite-dimensional system. Alpha 0 is everybody with everybody and so on. But still, what are the prospects of going to two-dimensional traps and things like that? John Bollinger was starting something like that. How does it look like?
Yeah, there's a different geometry of ion trap called a Penning trap. I didn't even mention this. Our trap is called an RF trap or a Paul trap. And it works best in 1D. It only really works in 1D because it has RF fields. It's a quadrupole. You can only get a null of an electric field in 1D. Not enough dimensions around to satisfy Gauss's law. But a Penning trap uses not RF fields, but a magnetic field. So the motion of a big string, a pancake of ions, they undergo cyclotron motion. And you have to keep, there's a lot of bookkeeping there, and they've done that at NIST. and they've done experiments with several hundred ions. They don't have individual addressing of those ions, and there are very soft modes in that system. Because you have a 2D pancake, there are rotational modes, shear modes. They're super low frequency. They're hot, they're noisy, and they have Debye-Waller factors, which basically the crystal, any coherent interaction is tempered by those factors. So the better way to go to 2D is actually to have individual atoms, one at a time, underneath some arbitrary geometry of electrodes. And the hard part there is that you want these ions to be close together, a few microns, but that means that they have to also be a few microns away from a surface. If that surface is room temperature, even if it's cold, you're in trouble. So the surfaces need to be, in our systems, they're more like 80 microns away. And if you're 80 microns away, your ions are 80 microns apart, there's no coupling. So it's a little bit tricky to work in multiple dimensions, and so far it really hasn't gone anywhere.
All right, let's take a break there, and we'll continue at 3:30-ish.